Give you a due date 2 weeks from now, and by hook or by crook it better be done, because if I'm giving you time out of class, I'm letting you out early to do it. And you can choose to go home and do it, you can choose to go to the computer lab and do it, the library, whatever. But if you choose to go home and ignore it for 2 weeks and not turn it in, do not. I'm a very nice guy, believe it or not. You believe it. There's no reason for you to think otherwise. Don't expect an extension on it. All right. So that's the big trade-off. And if you have any trouble with an assignment, you always let me know before the due date so that I can help you. If the due date comes and goes, and that's the first time I hear that you couldn't do an assignment, then the failing is on you. All right. So that's one of my only sticking points. That and labeling graphs. So anyway, determine if the angles are greater than, less than, or equal to each other. Right. So we have angle ABD and BAD. So the first challenge that comes into play for pretty much all of these, because in the next set of problems they're talking about sides, and like you kind of put it all together as well. You got to be able to identify what angle they're referring to. I know it's going to involve the vertex A, B, and then D, but specifically in that order. All right, so that's the key. It's got to be in the order in which they indicate the values. Yeah, that's fine. So what I choose to do is highlight the value, from vertex to vertex in the order that they indicate it, and then whatever the middle angle or the middle vertex is, that's the angle in question. So they're talking about this one right here. All right, so that's this guy. So then we're going to do the same thing. BAD. All right, so I'll do that in a different color. Starting at B, going to A, and then ending up at D. All right, so they're referring to this angle right here. All right, so you see that the angles are named with the same vertices plural of vertex, if you didn't know. So it's very easy to get them confused. You're talking about that triangle, it's just which angle are we dealing with, right? So now I just need to make a determination of which one's the bigger angle. Now you could kind of wing it and say, well, it's angle B because it looks bigger. It's angle A because of that. Like you can make up a reason. Slap a protractor on it and take a wild guess. In theory, you can't assume that the triangles are drawn to scale, but the reality is they're almost always drawn to scale. I remember when I would teach Regents geometry in high school, that on the exam, it would say triangle not drawn to scale. So what I did, I took it on faith for years, for like a solid decade. And then also all the years that came before it when I was in school. I just believed it. One day I was like, you know what, let me take a look. I measured with both a ruler and a protractor. It was totally drawn to scale. So what that means is that any student, when they needed to figure out the angles, the size relationships with the angles, they could have put a protractor on those angles, come up with a numerical value, and then just say, oh, that one's bigger than that one, so we're good. Right? So technically you can do that. The only issue that you're going to run into with me is if I ask you to justify it. Now here it's just saying which one's bigger, but if I say why, now you have a little problem here, right? So I will tell you that angle ABD is bigger than angle BAD. All right. So that's a big old greater than symbol in the middle. And the reason is because angles and sides have the same size relationships. All right, that's the gist of the rule. Is it the rule that, as you would find it in a textbook? I don't know. I don't read textbooks, so I wouldn't really know. I did at one point. We all had to start somewhere. The idea is that you have three sides, and there's a distinct size relationship. This one is smaller than that one, is smaller than that one. So the corresponding angles should also have the same size relationship. It's just a question of which angle corresponds with which side. Well, it's always the angle that's opposite the side, because this side only exists because this angle has opened up to a certain angular measure to allow for that length to exist. All right, I kind of equate it to casting a shadow, so the only way the shadow exists at a certain length is if the building existed to begin with to cast a shadow. All right, so the only reason this line segment exists is because this angle opened up to a certain width. If you think about an angle in terms of a width, allowing these two vertices to be connected. All right, same idea of what happens here. It opened up to create this line segment. This angle opened up to create that line segment. So it's always the opposite side.
So go back to your shadow. So your shadow would be longer than mine because you're taller than me.
Exactly. Exactly. All right. So you draw the conclusion right from that, and honestly, I mean, it kind of feels like common sense, and the issue with common sense in geometry, common sense is the most dangerous thing in geometry, right? So if I say prove that the following figure is a square, you would say it's a square. My reason is because it's a freaking square. How do you know it's a square? Because I looked at it, and it's a square. You know what I'm saying? So like the common sense, like you've seen squares throughout your entire lives. It's one of the first shapes you learned about, like when you were a small child. You know what a square is, but now you got to prove it. And so you're like, now you're going to tell me that I got to prove that this very simple figure that it exists, and why. It's kind of hard to wrap your brain around, but we'll get there. All right, so ADB, so I'll just rough this one out. ADB, I do not have a steady hand. I can't rough it out. I just can't do that. I'll use this red one though. Whoa. I do love it when people mess with my settings though. No, I'll just do it this way because it's so easy to see. No, I can't. I can't even make it out, so I'll just deal with it. We'll try it one more time. All right, and then I'll just do this one real quick. All right, so that's my ADB. The next one is BAD again. So B, A, I'll just try to draw it alongside it a little bit. All right, so it's a little tough to see, but ADB opens up onto a side length of 23, whereas BAD opens up onto a side length of 35. All right, so one has to open a lot more than the other in order to get where it needs to go. The one that has to open up more than the other is BAD. All right, so the first angle is going to be smaller than the second one. All right. Next set of problems goes the other way, where it's the same concept, but now we're identifying the angle corresponding to the given side. All right, so I have this guy here, LM. I'll just do that. And then I have this guy here, LP. And really, all you need to do is identify the angles that open up onto that side. All right, so if you have to open an angle up to get to the green side, it would have to be that 59-degree angle. All right, so that's the one that opens up onto that bad boy. And then if I need to open up onto the red one, it would have to be the 83. All right, so 83 is bigger than 59, so it would have to open up to a bigger line segment. All right, so therefore LP is bigger, meaning that LM is less than LP. All right, a big challenge that's going to come into play is not so much getting the answer as it is going to be to articulate your thinking in coming up with that answer. All right, because it really is a question like, how do you know LM is smaller than LP? Because of that rule you talked about that one time. All right, or just look at the I drew a picture. No, explain. Use words. All right, articulate your thinking. All right, and so we'll learn how to do that also. All right, we have CE, and we have CD. All right, now this is not designed to be a trick question, but it always tricks people anyway. Because you look at it and you see, I got side CE. Oh look, that's opposite an angle of 40 degrees. And then you see side CD, which is opposite an angle of 55 degrees. Oh, it's cut and dry. This is the bigger one. Very good. But something doesn't sit right. It doesn't sit right with me personally because I'm looking at the picture. So I never lose sight of the picture. So I'm looking at the picture, and maybe, I don't know, but it just kind of looks like they're around the same size. Maybe this one, maybe the red one's even a little bit bigger. Bottom line is getting me to kind of second guess it a little bit. And it turns out that that 40 is irrelevant. It actually turns out that this entire parallelogram, if this is indeed a almost parallelogram, quadrilateral, is irrelevant. Right? Because that size relationship only occurs for angles that exist within the same triangle. Right? So all of these, ignore this is like garbage. We don't need any of this. Cut out all the fluff. Just like for this problem, we didn't consider any of this stuff. And this one, we didn't consider any of this stuff. And for this one, we didn't consider really any of this stuff. All right? So it's only the values that are contained within the same triangle. So I'm going to do a quick 180 minus the 55 minus another 50. All right, so I'm taking 105 away from 80. That's going to leave me with 75 degrees. That's what this missing angle is here. All right, and so 75 corresponds to that red line segment. The 55 corresponds to the green one. 75 is bigger than 55. All right, so that's telling me that angle or side CE is actually the one that's going to be bigger. All right, so I said a little while ago that it wasn't designed to be a trick question. Honestly, I didn't make the question, so I'm sure it was designed to be a trick question. I don't think it should be considered a trick question because I don't think you should fall for that kind of trick. Right? I think you're better than that. Right? As long as you know this rule, and only that this rule applies within the same triangle, then you're fine. Honestly, I feel like we beat this concept to death, literally. I think the concept's dead. And I'm not sure what I was thinking when I created this. This one looks like it would take forever. And where I didn't make this one myself, I totally made this one myself. You could see, because it's not like perfect, you could see the extra nonsense there. I'll take this as a typo. Like this, I forget which, this is page 4. So on page 4, toss question 8. All right, so if anybody needs some typo bonus points, you submit that bad boy and I'll get you a point. This is actually for a different day. We can do it because actually it's going to tie in together with the tech assignment. So we'll do this page, then we'll take a little break, and then I'll go over the tech assignment, then I'll get you out of here. I'm not going to do all of it. It's just I'm going to kind of get you going in the right direction. All right, so the key here, and I know it got cut off at the top, I'll have to work on my converting of files. Regular polygons. All right, so regular polygon, you investigated this on the first day of class. This is a polygon where all sides and angles are congruent. I'll at least try to write it. Where all sides and angles are congruent. All right, and remember, congruent just means geometrically equivalent. All right, so it tells us that we don't actually have to know the numerical value in order to know that they're the same size. All right, now I know that there is 180 degrees in a triangle. All right, so if I add up all 3 angles in a triangle, I'm going to get 180 degrees. Now, a regular triangle is also known as equilateral or equiangular, right? But it's telling me that each one of these angles is going to be 180 degrees divided by 3. All right, so that allows us to draw the conclusion that angle A has to be 60 degrees. All right, and I'm going to kind of line this up with the examples that follow, because the triangle question corresponds with number 10. How many sides does a triangle have? 3. You got to start somewhere. It's not an attempt to insult your intelligence. Find the sum of the interior angles of a triangle. So it's 180 degrees. All right, and so the sum of the interior angles for that particular case could be, for example, that this pen almost worked. It was almost there. I'm just going to write 180 degrees just because I don't have faith that I'm going to be able to physically write more than that. All right. Now, that angle B is an exterior angle. All right. Exterior angles, interior angles, they add to equal 180 degrees also. All right. So angle B is going to be 180 minus 60. Well, it's going to be 120 degrees. All right. Second part of number 9 is talking about a regular quadrilateral, which is going to be a square. Okay, because if all sides and angles are congruent, the only way that plays out is if it's a square. Now, we know just based off of appearance, and also it's just a fact that you probably have been exposed to repeatedly throughout the years, that the four angles that make up a square are right angles, right? And those right angles will always be 90 degrees. All right. So here I'm kind of going the other way, where if I know each of these angles is 90 degrees, and there's a total of four of them, if there's four sides, there's four angles. If there's five sides, there's five angles. If there's 10 sides, there's 10 angles. All right. That tells me, going to number 11, four sides in a quadrilateral, we can expect 9 times 4, 90 times 4, which is 360 degrees. All right. The exterior angle still is going to be supplementary relationship. So 180 minus your known angle. Also going to be 90 degrees. All right, so the exterior angle of a square or any kind of rectangular quadrilateral is going to be 90 degrees. All right, but now what we want to do is try to project this out to other types of polygons and see if we could generalize this. Because you don't want to actually have to say, okay, well, I know that there's this, that, and the other thing, because then you find yourself memorizing something for every single geometric figure. All right, so couple of ways to go about doing it. One would be to kind of see if we can make a determination of whether or not we could figure out what the exterior angle is and then work backwards from there in order to figure out the interior angle, right? Because there seems to be some kind of relationship between the sides, the angles on the inside, and that exterior angle. But we could do it for one more case and see if we can really kind of tie it together. All right, so there are, and I'll just give this to you, there's a total of 540 degrees in, this is a pentagon. All right, total of 540 degrees. Now, if I take 540 degrees and divide it by the 5 congruent angles here, I'm going to get a measure of 108. So 108 degrees. The exterior angle is going to be 180 minus that. So 72 degrees. All right, and so this, I think, is probably the most interesting part of it. I kind of pride myself on the fact that I can understand other people's math. You know, when they tell me a rule, and like, oh, that's pretty cool. I understand. I get it. There are some things where it's like, oh, that's cool. I never would have thought of that, right? And this falls under that category. So it turns out each one of these exterior angles is the result of taking 360 degrees, and we will prove this later in the course, taking 360 degrees and dividing it by, I'll call it n, where n is the number of sides, or angles, because they correspond. But when I say what's a pentagon, or how many sides does a pentagon have, you know, what's an octagon, an 8-sided figure, most people think in terms of sides. So it makes sense to do that. All right, so if I take 360 and divide it by n, I'm going to get each one of these values. All right, it just varies from problem to problem. All right, there are 3 sides here. 360 divided by 3 is 120. 360 divided by 4 sides, 90. 360 divided by 5, 72. So then we get to a hexagon. So we're working backwards. 360 divided by 6 is going to be 60 degrees. So that's the outside angle, the exterior angle. Because these two angles are supplementary with one another, it's not even worth drawing the diagram. It's just terrible. They're supplementary to one another. I know that all I have to do to figure out G is take 180 and subtract from it 60 degrees. And I'll get each one of those interior angles. Now, if I want to know how many there are in total, I have 6 of those angles. So to figure out the total angular measure for all of those angles, I would just do 120 degrees multiplied, I'll just use the multiplication symbol, by the number of angles, and you get 720 degrees. All right, so it's kind of a nifty trick. Tricks are great, but we do want to try to understand where these tricks are coming from. So I'll show you, well, it's a visual trick as opposed to a numerical one. So if you start off at a vertex, and some of you may have seen this one before, I think it's a pretty cool one. Start off at any one of the vertices, pick one, and draw straight line segments to every other vertex. What's going to happen is you're going to create a certain number of distinct triangles. All right, and how many degrees are in a triangle again? In a triangle? 180, right? And how many triangles do I have here? 4. And what do you think 180 times 4 is? 720. All right, and you can do that with any polygon. Also falls into the category of stuff I never would have thought to do. But it's kind of cool when you see it, because here I get 3 triangles, each one valued at 180. 180 times 3 is 540. Here, I can only get, and you can pick any vertex, it doesn't matter which one. I can only get 2 triangles, 180 apiece, 360. And a triangle's a triangle. So what we're going to get from this is, let's learn everything we can about triangles, because it seems like everything else is made up of triangles. All right? You might say, well, what about circles? Or you might say, it's 730, who cares? There's all sorts of possibilities. All right, but let's say you were thinking circles. They're not made up of triangles. Well, a circle is an infinitely many-sided polygon. So hopefully you kind of see it. As I keep adding more and more sides to my polygon, it does appear to get more and more circular. If I could ever get infinitely many sides into that polygon, what I would actually have is a circle. Right? So a circle by definition is an infinitely many-sided polygon. Right? So know everything there is to know about triangles, and you know everything there is to know about geometry. All right? And honestly, when you think about it, geometric figures come down to a few important characteristics: area, length, and angular measure. Right? So there's not really much to learn. Right? So in number 12, when it says how many sides does a decagon have? Well, deca, like decade, 10. I could use that little shortcut, which is to say, let's take 300, because I don't want to draw a decagon, right? Slash, I can't, physically can't. I'll take my 360 divided by 10. So that's 36 degrees. That's the exterior angle. I know that the supplement of that, 180 minus 36, 144 is going to be a single interior angle. And I'll jot down that this is an angle. And so is this. And so then all I have to do is multiply that by the number of sides. So I'm going to take that and multiply it by 10. Or angles. So 1,440 degrees is going to be the sum of the interior angles. All right, so number 13 is the grand finale, the pièce de résistance. That has a certain je ne sais quoi. How many sides does an n-gon have? Well, a decagon has 10 sides. A trigon, also known as a triangle, has 3 sides. An octagon has 8 sides. But after you get past a decagon, they have names for them, but they become so cumbersome that we don't call them by dodecagon and all that stuff. We just start calling it by the number. So we'll call it a 23-gon or a 72-gon. So the number of sides an n-gon has is, you guessed it, n. So when I want to find the sum of the interior angles of an n-gon, I'm going to follow this exact same process. Except everywhere I have a 10, I'm going to swap it out for an n. So we're going to get an answer that has an n in it. So there's a little bit of algebra. A little bit. Try to stay away from that as much as possible. 2 classes that I almost apologize for doing algebra in would be this class and statistics. Right? Because I feel like there's really not much need for it, but sometimes what are you going to do? Sometimes you just can't get away from it. So I'm going to take the 360 and I'm going to divide it by n. I'm not going to get an answer for that, right? Because I don't know what n is. Except to say that I'm going to just write it as 360, a fraction, 360 over n. Like 1 divided by 2, I just write it as 1/2. Right? That number then gets subtracted from 180. So 180 minus that 360 over n. All right, so that was my first step, corresponding with this first step, and my second step corresponding with this second step. Then after that, I multiplied by 10, so that was this step here. So that's what I'm going to do here. I'm going to take that result and multiply it by 10. So 10 times everything I just had there. So 180 minus 360 over n. Now you could simplify it if you want. There's actually a fairly clean simplification of it. It is not even remotely worthwhile. So I would suggest that you don't bother. Oh, sorry, n. Thank you. Good catch. Yeah, actually, if it was a 10, then it would be worth simplifying. In this case, you could. Doesn't really, I mean, yeah, I mean, it would just be 180 n minus 360 if you really want to know. But it's really not necessary. You just leave it like this. And so we could test it out. Let me see if I can easily access my calculator. So n, so last problem we did was 10 times 180 minus 360 divided by 10. Got the 1440. All right, do it with a triangle. 3 times 180 minus 360 divided by 3. 180. Do it for whatever you can think of, and you'll get it. And so what we just did here, whether you wanted to or not, you know, like I don't know if it was on your list of things to do coming into class today. Like I really want to do a mathematical proof. But what we did was we just invented a rule. Based off of a pattern that we observed, we derived a rule that could be used in any situation. All right? So if I need the sum of the interior angles of any kind of polygon, I now have a method for figuring this out. And I also have a method for figuring out a single interior angle. I would just stop short of multiplying it by n. All right? So a lot of good things going on with a problem like this. All right? So numbers 14 and 15 are really just taking that concept. Well, 14 through 17 are either drawing the diagram and so on, or using this brand new rule and kind of working with it in different ways. All right, so I'm going to put stars on these and let you have time to practice them. Well, have time to practice them means like take them home and do them on your own. Yeah, because we're going to take a break now, and then we'll come back and we'll talk about that tech assignment, like I said. Okay, so this is page 5.